So welcome to the continuing lecture on pulse code modulation. The previous session we have defined what is pulse code modulation. Now we'll see how a pulse code modulation works in practice. Let us see the block diagram of a pulse code modulation system. Here we give the input as an analog signal to the sampler. After sampling, quantization and encoding, we get the digital data as the output. The quantized signal will be a digital discrete signal which is not continuous, which is having sufficient values for each point in the amplitude. We have two, it is two dimensional. So both the dimensions, one will be the x and the other one is the one will be the x and the other one will be the amplitude. This will be the output PAM signal consisting of a digital data which has only zeros and ones. So the waveform representation in your examination answer sheets, you must draw the waveforms and write all the necessary equations whenever a question is asked. So this will be the analog signal. This will be the condition when it is ideal, sampled, natural sampling and flat top sampling. Three different sampling methods for pulse code modulation. So what do you understand by sampling? What are the different types of sampling? These are all possible questions in your examinations. So the next important, very important theorem and very famous Nyquist theorem, which defines how you have to sample an analog signal. According to Nyquist theorem, the sampling rate must be at least 2 times the highest frequency contained in the signal so that this particular signal could be reconstructed in the end. So what is Nyquist theorem? Nyquist theorem states that the sampling rate should be at least 2 times the highest frequency contained in the signal. That means Fs is equal to 2 Fm at least, minimum. Fs is greater than or equal to 2 times Fm, where Fm stands for the highest frequency component in the signal. And this is a very important theorem. This has lot of practical relevance also. There is sufficient proof for this, but we'll not be dealing with the proof because it is beyond our syllabus. Nyquist theorem states that the sampling frequency or the sampling rate should be at least 2 times the maximum frequency component available in the analog signal. Extremely important theorem. So let's see certain definitions with respect to Nyquist theorem. For any signal of bandwidth W hertz, the sampling rate of 2 W samples per second is required for a signal bandwidth of W hertz, and this rate is called as Nyquist rate. Inverse of this or reciprocal of this is known as Nyquist interval. We have two different terms. One is called as the Nyquist rate, the rate at which the sampling occurs. and we have Nyquist interval, the time gap between two signals. Next important definition is aliasing. Aliasing means aliasing refers to the phenomenon of high frequency component in the spectrum of the signal seemingly taking on the identity of lower frequency in the spectrum of its sampled version. Aliasing in general means we are giving a different frequency interval for the higher frequency component so that we can analyze the signal in a better way. Aliasing is a very common question that can appear in your exams, and aliasing is one of the drawbacks that we will be facing while we are sampling a signal. What is meant by aliasing? Aliasing is the phenomenon in which the high frequency components in the spectrum of the signal is being given the identity of another frequency, a lower frequency component within the spectrum when it is sampled. So, if you have a sampled output, after the process of sampling, the high frequency components is linked with a lower frequency component. What is aliasing is given here and how it is being graphically represented. See, you have a high frequency component that is being converted into a that is being linked with an lower frequency component. This process is called as aliasing. So now this is a graphical illustration of Nyquist criteria. You can see that there is the highest frequency F min to F max. Nyquist rate is defined as 2 times F max, and the frequency between F max and F min is passed through this band pass filter so that you get a band pass signal that is between F min and F max. Next, what is meant by quantization? We know that for pulse code modulation, we need to sample the signal, and the sampled signal will be given as an input to the quantizer. What will be the quantization phenomena? I've explained to you very clearly what is quantization in the previous class. Sampling results in a series of pulses of varying amplitude values ranging between two limits, that is a maximum and a minimum value. The amplitude values are infinite between these two limits. So we are mapping this infinite continuous amplitude values to a set of digital values, and that process is called as quantization. Quantization means, all of you stop writing and listen to me. You have a signal like this. Say for example something like this. What we have done is that we have sampled the signal. We have sampled the signal and we have created points like this. In quantization, what we are doing is that we are assigning a digital value to each of these points here. We'll call this as zeros and ones. A set of zeros and ones is called as a symbol. It can have n number of bits. Okay. So this delta is the height between two possible digital values. Okay. So here you have the signals, that is sampled and sampled points. At each point value you have a symbol assigned to that particular point. That is called as a symbol, and a symbol consists of a n number of bits. That means every symbol will be having some zeros and ones. Is that clear? This process is called as quantization. So what is quantization? Quantization is the process of transforming the sample amplitude m nts of a message signal m of t. Quantizer input is from the sampled signal. Okay, already you have sampled the signal. That is why the sample amplitude of m nts of a message signal m of t at a time t is equal to nts into discrete time, discrete amplitude taken from a finite set of possible amplitudes. So explanation for what is quantization, what I've just now explained to you. Let the amplitude range of the continuous signal be partitioned into n quantization levels, or L intervals, where L will be defined as 2 raised to n, where n is the number of bits per symbol, where ith interval denoted by tau and is determined by the decision levels, also known as threshold levels, D1 and D2. As per what I have explained, what happens if it is in between these 2 points, it has to make a decision on whether it has to be on the upper or the lower side. Okay. So dou D1 between M and D, L plus 1, where L is 1 to capital L. Then the quantizer represents all signal amplitudes in the same interval tau by some amplitude T1, which is the element of tau. That means that each level or each quantized point is represented to be an element of the entire interval of quantization levels. And this is also known as representation level or reconstruction level. The spacing between two adjacent decision levels is called as step size delta, and delta value is max minus min by L. If the step size is the same for each interval, then the quantizer is called as uniform quantizer. We have two types of quantization. One is a non-uniform quantization and the other one is the uniform quantization. If it is divided into equal intervals, it is called as uniform quantizer. What we have studied so far is a uniform quantizer. We have non-uniform quantization also. The uniform quantizer is the simplest and the most practical one. Besides having equal decision intervals, the target level is chosen to lie in the middle of the interval. So let us see the graphical representation of how a quantized signal should look like. You are given the input waveform in a dotted lines, and the quantized signal and the error or the difference between 1 and 2 and the quantization error is also given. Please note down the quantization in graphical representation. So what are the different types of quantization? If the quantization levels are same, it is known as uniform quantization. And if the quantization levels are not uniform, it's called as non-uniform quantization. Write down what is uniform quantization. If the steps are uniform in size, the quantization is known as uniform quantization. The input and output characteristics of a quantizer looks like a staircase. In uniform quantization, we have two types. One is called as mid-thread and the other one is called as mid-rise. Mid-thread because the origin lies in the middle of the thread of the staircase like a graph, and mid-rise when the middle of the rising part of the staircase looks like. It depends upon the origin, that's it. We have two types, mid-thread and mid-rise. We'll graphically study how a mid-thread looks like and how a mid-rise looks like. Among the common questions that you may need to face in your exams, it will be different types of quantization or different types of uniform quantization or whatever it is, depending upon the question paper and the marks. So what are the two different types of uniform quantization techniques? Mid-rise and mid-thread. So we can represent graphically mid-rise and mid-thread. In mid-thread you can see that there is only difference here is that you can see that in the origin you have a flat thread. Here you have the rising one. So there is a difference between a mid-thread and mid-rise quantizers. And based upon this, we have a different set of characteristics which might keep changing accordingly. What is quantization noise? Inevitably, whenever you quantize a signal, you have an error happening right from the original because there is a small gap. This error is an undesired signal and is known as quantization noise. So when you quantize a signal, naturally you will have some errors because we are not taking every values in the continuous signal. We are taking only some values. So you have a difference from the original signal. So now let us mathematically derive or mathematically understand what is quantization noise. Let us denote the transfer function of a quantizer to be G, which maps the input of the random variable M to a continuous discrete random variable B. Their respective sample values are M and B and are related by a nonlinear function, which is the transfer function G. Let the quantizer input M be the sample value of the zero mean random variable M. Then let the quantization error denoted by Q of the sample of the value Q will be M minus V. I hope you are able to understand what is meant by quantization noise. So we consider two random variables, input random variable and the discrete random variable, which is the output of the quantizer. The error or the quantization noise Q is defined as M minus V. Quantization noise derivation. Now we are considering M to be a continuous amplitude symmetrically occupying the range between two values. One is a max minus M max and M max. So what will be the step size of the quantizer? The step size of the quantizer will be M max minus M max by 2. That is 2 M max by L. Sorry, not by 2, by L. So the step size is given by 2 M max. We are considering uniform quantizer because we are dividing it into equal halves. So L is the quantization levels or total number of representation levels. In that case, the PDF of the random variable Q is therefore given by FQ of Q is equal to 1 by delta, delta is the step size, minus delta by 2 to delta by 2. In between those two values lies Q. Q is the random variable. So with this assumption, what we have done in the previous slide, we are going to calculate quantization error. The mean of quantization error is 0. So the standard deviation sigma square Q is equal to minus delta by 2 to delta by 2 Q square FQ of Q dQ. So on solving this integral, what we'll get? We'll get delta square by 12, or that is equal to delta square is nothing but 2 M max by L. Delta is 2 M max by L. We have calculated in the previous slide that the value of delta is equal to 2 M max by L. So on substituting that here, you will get M max square by 3L square. Each target level at the output of the quantizer is typically encoded or represented in the binary form or as a binary string. So the number of quantization levels are usually taken to be the power of 2, 2 raised to r or 2 raised to n, whatever we call it, where r is or n is the number of bits that is needed to represent each target level. Now let's substitute L is equal to 2R in this equation. In this equation, let us substitute L is equal to 2 raised to R, where R is the number of bits per symbol. Next is a very important concept called a signal to noise ratio, SNR. With the mean of the quantization noise being 0, its variance is same as the mean square value, that is, we calculated sigma q square by substituting L is equal to 2 raised to R. So from this, we are calculating signal to noise ratio. Okay. Since the message sample M is 0, mean random variable PDF FM of M, the average power of the signal is equal to the variance. Okay. So SNR signal to noise ratio after this quantization of the input or the message signal, that is denoted by SNRQ, is given by 3 sigma m square by m max square into 2 raised to 2 raised to r. In other words, or this is equal to 3 into 2 raised to 2r by f square. The parameter f in this is known as the crest factor of the message and is defined as the peak value of the signal M max by the RMS value sigma M. So if P denotes the average power of the original message signal M of t, that has to be transmitted, the output signal to noise ratio of the uniform quantizer is given by SNRO is equal to P by sigma q square. That is 3 P by M max square into 2 raised to 2R. So what is R? R is the number of bits per symbol, right? This shows that output signal to noise ratio of a uniform quantizer SNRQ increases exponentially with the increasing number of bits per sample R. Derive the relationship of SNR with R. Signal to noise ratio increases with R exponentially. So here you can very easily imagine with your common sense itself that when the number of bits per symbol increases, the signal strength or the quality of the signal naturally increases. What is most desirable, high SNR or low SNR? Signal to quantization noise ratio SNRQ is given by sigma x square delta square by 12 or sigma x square by sigma y square. Solved problems. A message signal AM cos omega mt sampled and applied to a quantizer with Q permitted quantization levels fully loads it. Find the signal to quantization noise ratio at the output of the quantizer. How you will find this?